everyone. My name is Natali or Natali Soler Matubaro. I'm a PhD student at University of São Paulo, Brazil. And right now I'm here at Flatiron Institute as a pre-doc. So today I'm here to talk to you about how to constrain omega matter with galaxy information, galaxy phase space information. And then that's it. So this work started with the question, is there an optimal way to do parameter inference? And this is a work that has been done by me and all these amazing people here. And then, so let's go. The way that we're trying to answer this question is trying to do galaxy field level likelihood free inference. So imagine that we have a bunch of galaxies and all that information. So we're trying to translate this information in graphs. And graphs are very a good idea to contain all this information because they can be a natural representation of the cosmic web. And why? So a graph can be think about as made of nodes, which for us are going to be the galaxy properties. And then they are composed by edges, which are the connections between the galaxies that we obtain using the galaxy positions. So then we have our graph. And in this work, we are obtaining our translations of our galaxy catalogs into graphs, linking the galaxies which are inside, or you can imagine that we have this red galaxy here, and then we grow a sphere around this galaxy. And if these other galaxies are inside this R-link, they are connected. And in this work, this R-link is around 1.25 megaparsecs per H. And then these graphs are going to feed our black box of machine learning, or graph neural networks, which are pretty good to deal with regular data. So we are inferring omega matter, and this is a really good way to do this because it's a fast method, and it's a method that we do not have to impose any cut and scale. And then, let's talk about graph neural networks. So I believe that my role here should try to explain for you what is behind this black box of machine learning. So we are feeding these graph neural networks with our galaxies translated into graphs. And then we have done this implementation using a message passing scheme, which means that we have our blocks in this architecture. And the idea is that we are going to update the values that we have in our nodes and in your edges. And that's why they are changing their colors from here to here. And after some layers, okay, we will end up with some representation of an updated graph that should contain all the information related to small and larger scales. And then we are compressing one more time all this information in a simple multi-layer perceptron, which is responsible to predict the first and the second moments, okay, of the posterior distribution of omega matter, so the mean and the standard deviation. So in this work, we are using the Camel suite, which Megan presented and given some details this morning. And then this Camel suite is amazing because we have many hydrodynamical simulations of smaller boxes of 25 megaparsecs per H, but it's really good because we have like smaller boxes, we can have many boxes. And in these variations, we are varying the parameters, the cosmological parameters, omega matter and sigma H, and the astrophysical parameters, two related to supernova and two related to AGN. And okay, we have different subgrid physics models in this suite. Right now, we have Astrid, Illustrious-NG, Magneticon, Simba, and Swift Eagle. Not all of them are available for everyone yet, but they will be soon. And then, so it's important to say that here we have the Sobel sequence 28, or SB28, which is nothing more than the same subgrid physics for Illustrious-NG, but varying more than these 6 parameters that we can see here. As the name says, we are varying 28 parameters. 5 cosmological, and the rest are astrophysical parameters. So this is our data set. And then in this work, we found one BESS model. And this BESS model was built using the galaxy information, which are the 3D position of the galaxies, and then the Z component of the velocity. So why DESI component? Because in this work, we want to give the first steps in the direction to apply the machinery to real data. And because in the real world, we only measure the velocity in the line of sight, the radial component, we have only one. And for simplicity, we are using the DESI component of the velocity of the galaxies. And then in this work, we want to try to see and to obtain a model which is robust. And then we have to choose one subgrid physics model, and then we are choosing in this best model the Astrid hydrodynamical simulations. So the idea is try to test this model and see if you can overcome the difference in these 5 subgrid physics models to predict omega matter. And the answer is that, yeah, we have a model which is pretty much robust. And then here you are taking a look at one of our best results, which follows for our best model. This is a sanity check because you are taking a look for a model trained on Astrid and tested on Astrid. And as Festo presented for you, this is a famous plot where we have the predictions versus the truth values. And then the idea is that we want to be as close as possible to this gray line, this one-to-one correspondence. So as you can see, just by eye, all the points are following this gray line here. And if we take a closer look, we can see that all the scores are pretty good. So RMSE is low, is a low value, R2 square and PCC are close to 1, which is good too. Our model is not biased. Our relative error is around 12, which is good. And then our chi-square is 1.64, which means that we are not only predicting pretty well the mean values, but the standard deviations too. So these error bars that you can see. And then, okay, this is a sanity check. The model works. So let's see what happens when we try to see if this model is able to extrapolate their predictions. And here you are taking a look at our predictions for Illustris-NG, Simba, SB28, Magneticon, and Swift-Eagle. So these plots, you already know how it works, okay? I told you in the previous slide, but here you are taking a look at truth minus inference, and the points are just displaced in a random order. So, okay, just by eye, all the predictions are pretty good for all these different models, and this is not an easy task. Most of the times, we train your machine learning model, and then you change your data set, and nothing works. But here, this model is working, and we are showing that this method overcomes all the difference in this subgrid physics. So taking a closer look, you can see that all the metrics are pretty good too. And then we can say, okay, we achieved a model which is pretty robust. And it is robust, even trying to vary these other cosmological and astrophysical parameters that the model has never seen before, because it was trained on Astrid that varies only that 6 parameters that I told you previously. And then it still overcomes another thing, which are a difference in the halo or sub-halo finder that we use, and that is different, which here is Velociraptor in Swift-Eagle, and now the others, the halo sub-halo structures were found with subfines. So why the model trained on Astrid is so good? We have 2 ideas to say why this is so good. First is because if you take a look at the number of the galaxies versus the values for omega matter, you can see that, okay, in the case of Astrid, we have different boxes which contains the number of galaxies goes from 40 to more than 1,000. And then a model trained on Astrid will see, have seen like boxes with this variation of number of galaxies. But a model which was trained on Simba or Illustris-NG have never seen boxes with this smaller or huge number of galaxies. And okay, we can say that Astrid allows us this broader variation in the number of galaxies. The other thing is that in the case of Astrid, it produces larger variation in some galaxy properties, which does not happen for the others. And then that's it. Astrid is amazing. And okay. In this work, we have tried some other things. The first thing was training the model on Simba and Illustris-NG. And as I told you, the model trained on Astrid is pretty better. So here you are seeing the truth minus the inference for a random point for a box for Astrid, Simba, Illustris NG, SB28, Magneticum, and Swift Eagle. The same colors that I used in the other slides. And then these are the results for a model trained on Simba and for a model trained on Illustris NG. And the idea is, okay, it works pretty well when we try to see what is happening in your sanity check or close to this, right? But when we try to see the robustness power, the extrapolation power of the model, it doesn't work, especially for Magneticum. So, okay, we tried to do another thing, which was trying to improve this machinery. So I told you that we are using only the galaxy positions and velocities. And then we included the stellar mass as a node information for our graphs. And when we have done this, we take a look of our sanity check. So the model trained on Astrid and tested on Astrid, and everything improved. All the metrics improved, or almost all of them. But when we try to see the predictions in the other simulations, everything basically breaks down. So it doesn't work anymore. So when we include the stellar mass, we are close to the difference in the subgrid physics, okay? And then we are not able to extrapolate. And then we try to see what are the, what was the most important galaxy properties that we're using. So we trained a model using only the position of the galaxies and using only the velocities. And in both cases, all the error bars increased, and the model is not robust anymore. It doesn't work for when tested in the other simulations. So, okay, but what about trying to apply this machinery from real data? So we are giving the first steps, baby steps still, but okay. The first thing is that we have to see if our model can overcome these changes in supersample covariance, because we trained this machinery in boxes from camels, so boxes of 25 megaparsecs per age. So what happens when you try to apply this same machinery in subsamples of a big box? So we have done this using Illustris NG 300, and then the model seems to kind of works. It's important to say that we noticed something important related to the periodic boundary conditions. Megan told this this morning too. And then, okay, we are considering periodic boundary conditions in your best model, but to see if it works in smaller samples of this big box, we turn it off, the periodic boundary conditions, to our graphs, to build our graphs, and then to build our graphs to train the model. And then we tested this in Illustris NG without the periodic boundary conditions. So the model kind of works, but we still don't have like the best metrics, okay, the best scores. When we remove some points, some of these random smaller boxes inside this big box, we saw that these scores improved a bit, not a lot. So we still have to analyze how to deal with the supersample covariance, but it seems it works. And then we have to take a look on the errors that we have in the peculiar velocities. And then we have to see that, okay, in the real world, we don't have access to all the galaxies that we wanna, and then we have to take care of selection effects. So these are next steps. And okay, this work was done together with this companion paper from Helen. So the title is Universal Equation to Predict Omega Matter from Halo Galaxy Catalogs. And then the idea is that she's using symbolic regressions from GNNs to constrain omega matter. This method is trained on Halo catalogs using Halo's velocity modules and positions. And these are the first step in the direction to try to get a physical interpretation behind this success of these GNNs. And then this model is robust, not only changing these any-body simulations, changes to others, but it's working on the galaxy catalogs too. So that's amazing. And then the takeaway messages of this work are, first, we obtained a method to do cosmology, in other words, to constrain omega matter using only galaxy positions and velocities, the Z component. Second, we are able to constrain omega matter for 5 different hydrodynamical simulations. If you take a look on the relative errors or in the chi-squares, it works pretty well for Astrid, Simba, Illustris NG, SB28, Magneticum, and Swift Eagle. And then in this work, we're giving the first steps in the direction to possibly apply these to real data. Thanks.
Questions?
Hello, it's Santi here again. Just I'm always very curious about the. Hello, can you hear me?
Yeah, maybe easy.
Okay. Just curious about what is fundamentally like different from sort of the cosmological probes that we have been doing, because we also look at the density field, the velocity field. Is there any information that you are extracting that is fundamentally quite different from what we have been doing with the density field and velocity field? But of course, here you're looking like quite locally. I'm just wondering, is there any subtle information that is more than that?
What do you mean? Because the information here is coming basically from the galaxy position and velocities.
Right. So put it more concretely. So if I do a joint analysis on top of the graph on the galaxy, and I also do a density field and velocity field with like camel, do I get a stronger constraint than just the density field and the velocity field?
Yeah. We show that only using velocities or only using positions, the constraints are not so good. And then we need to have both in this work to define these constraints.
But more concretely, if I do a density field and velocity field study in cosmology and do
using the usual summary statistics.
Right.
Oh,
so
okay.
let's say you do an SBI on the density field and velocity field, and now on top of that, I also like include this information. Do you get a stronger like constraint?
Yeah. Well, it's a bit different. So here we have another proposal, right? But if we only use like this other machinery, I mean, they are different approaches, but I don't know if I got your point properly.
Okay. Thank you.
We can talk more later.
Yeah, for sure.
Do you want to say?
Hi, Natali. Thanks a lot for the talk. This is Martin Ray speaking. Do you know why the Astrid model is generating so much wider predictions? Is this something physical about the model, or was it designed to scan much wider parameter space compared to the other ones? Well, why does it generate all of these new training points that are so far outside the other hydro models?
Okay, you have some guesses related to the wind speed in this model, but the best person to answer this question is the person which is the specialist on Astrid, which is Eugene. But the idea is that in all these different chemo suites, they are designed to be almost the same when you take a look at the fiducial models. But taking a look at the variations of all the parameters, which are the same for all the simulations, these variation in the galaxy properties are larger than the others.
Risa Wexler, really nice talk. Thanks. Very interesting direction. So 2 questions. One is, do you have any sense of where the fundamental systematics limit of this technique will be when you actually do apply it to real data? And then it's a kind of related question, to maybe trying to reframe that one. What information do you think exists in the galaxy distribution that this isn't capturing?
Okay, so the first question is, the limitations. Well, we have trained our models in really small boxes. So we have like a number of galaxies which this works, which follows around 1,000 of galaxies, okay? And for smaller samples. So we have to see if when we apply these to real data, it's going to work. Okay, only taking around this number, or around like 1,000 of galaxies. Apart from that, we have the limitation related to the smallest distance for galaxies that we have in Astrid simulations, which corresponds to k of 10 to the minus 1 kiloparsecs, something around this. And well, the second question, can you repeat, please? I forgot.
What information do you think exists in the galaxy distribution that's being used by current cosmological probes that isn't included here?
That isn't?
Yeah.
Oh, we could include a lot of things, right? But when we include a lot of things, for instance, other galaxy properties, we can say that our model is not robust anymore. So if it doesn't work among the different simulations, is it going to work in the real scenario? So
let's discuss it offline. I think the same.
okay.
Yeah, thanks very much for the talk. Smart work as company. I have so if I understand properly, things work because Astrid has a wider parameter variation, and then you're englobing all the others.
Yes.
So 2 comments there. So this doesn't mean that it will work on data, no? Because, still you are finding a model that covers all the training range of all the others. So I agree with that it's a sign of robustness, but, data, if you're also showing that as soon as you are a bit outside of this wider parameter range, it doesn't work.
Yeah.
And so there's a risk that in the data you still have this issue and then it won't work.
Yeah.
And just wanted to comment, I mean, you can comment on that. And the other thing is, okay, so what you need, I understand, is having a wider variation of parameters. So if you take, for example, the illustrious TNG model, and now you're doing camels, so now do a much, stronger or, dramatic variation of the parameters, you are able to englobe everything again in the illustrious TNG model and make it work for all the others, or, or it's too far away to do that.
Oh, we do have this, right? We do have this in SB28.
Okay.
We have
Yeah, that's why I'm asking. And if you do that,
then this test.
And it works or not?
It works.
Okay.
But the model trained on Astrid works better, a bit better.
Okay, but so this means that you can extend all other models ideally and then make them work on all the others. It's just a matter of probing a wider parameter range of the baryonic physics.
Yeah, I would say that.
Even if it makes completely unphysical universes, which is interesting.
I would say yes, but I can give you this answer. Just
yeah.
Doing this, right?
Super interesting.
Okay, hi, Megan Tillman. Just a quick question. So you were talking about limited by the box size of the simulation. Could you train on the entire CV set of one of these suites, and would that up the sample size, or is that not?
On the entire CV set, because the entire CV set has only 25 boxes, right?
Yeah, but are you just training on one box right now, or are you already
No. Sorry.
Oh, you're training on the LH set.
Yeah, we are training the
I
LH set. Then. Yeah, sorry.
Okay, I revoke my question.
Yeah, sorry. I have never done.
What a fantastic talk. Thank you, Natali. I had a question. If you use number densities instead of if you use number densities instead of stellar mass, is that helpful in the sense that number densities might correlate with the halo mass in fixed cosmology?
Yeah, you mean like selecting boxes according to the number of the galaxy?
No, so instead of using a stellar mass directly, use the cumulative number density corresponding to that stellar mass in that box. So instead of, I don't know, 10 to 10.5 solar masses, you would say there are X number of galaxies that are more massive than this in this box, and use that number like the rank order in stellar mass or a number density in stellar mass as opposed to the stellar mass value itself.
Okay, as node information for each box. So in some sense, I didn't mention this, but we are using the number of the galaxies per catalog as a global information for each one of the graphs. Yeah, I didn't mention this, but okay, this is another information that we are using. So if you're already using this and we include this information as node information, I believe it's going to be the same, almost the same. But trying to replace this information, like the stellar mass information to the number density, yeah, it should be a good test, but we have to do this to see if we are achieving like this difference in the subgrid physics or not. But it's a good test. Thanks.
Hi, Francisco Castander. If I understood correctly, you are using a linking length to define your graphs.
Yes.
And that basically imposes a scale that you're going to study. Have you tried changing that linking length and how your statistics change, or robustness, or your performance?
Yeah. The linking radius is really important. So this is the way that we build the graphs, right? And then this for us is a hyperparameter for this machine learning stuff. We have a range of variation, and we're finding the best model, changing these values in this range. And this is one of the best, like the most important parameters. But in all the models that we find, the best models for each one of these tests that we have done, this R link is around 1.25 megaparsecs per age. And then if we go like far away from this value, the results change. So the predictions are not so good. But yeah, this is the best value in all the cases, doing this hyperparameter optimization.
Chris Lovell, thanks for the great talk, Natali. I just wondered if you kind of related to Peter's question, are there some summary statistics of the graphs that you could maybe extract that would show this, that are, I guess, insensitive to the variations in these different parameters that might help to explain why this works for, say, Astrid, where the feedback seems to have a huge impact on the number of galaxies? So yeah, my question, I guess, is, yeah, are there summary statistics of the graphs that you could extract that might give you some insight into why
that I could extract from the graphs
to make this a bit more interpretable?
Because we are translating the galaxy positions into a graph, right? And then this is our input. So if we try to, take it's doing like the traditional statistics, right? I mean, it's almost the same because it can go forward and back from the galaxy catalogs, but it's going to be the same, right? I mean, because we are translating information from the galaxy catalogs into the graphs. And if we just come back, we're just coming back to the information from the galaxies. But okay, we can try to. Yeah. Okay.
Things like this that might help, elucidate why this works.
Mm-hmm. I see.
We have, maybe I can quickly. So we have formula that we apply to the GNN. We don't understand the formula as well, but it's not doing something trivial. It's doing some clustering.
Yeah, but it's not the final answer to say it's clustering or it's.
Can I just quickly comment on that? Because I feel like there's a easy thing you can test, which is just comparing graph neural network with DeepStat. So DeepStat is just looking at the particles without doing the message and passing, because most of the cosmology and.
But we do DeepStat here.
So I guess the question is, like, if you do a DeepStat, like, do you get the same inference? So if you get the same level of inference, meaning that most of the information is either in the number like statistic or cosmology.
Yeah, but we show that when we do this DeepStat model, which follows for these plots here. Yeah, I didn't put the name, sorry. Okay. Because I would like to try to.
So the graph is more powerful than DeepStat.
Yeah. So in the case that we are using only the velocities, we have our DeepStat.
Okay, that's quite interesting. Thank you.
Yeah, sorry. Sorry, just to follow up on what Johan saying was asking about. So when you're only using positions and velocities, you don't have any edges in your graph. That is just a set of points with just positions and velocities.
No.
Okay.
This is only in this test. In the usual graph. So here I'm presenting another test. In the usual graph, we are finding the connections according to the positions of the galaxies. Oops. Sorry. When we are building the graphs. Here.
Yeah. So I'm with you so far. I think the thing that Yuan Sing was asking about before, and I just want to clarify that point, is if you remove all of the edges in your graph, how does your network perform then? Keep all the same features, remove all the edges. What happens then?
So what do you mean keeping everything? Because
keep all the halos.
Yeah, we
all the
did this,
edges.
yes, but we showed that our model is not robust when doing this.
We have this, so it's a deep set, and we only have velocities because you remove the position, and then it doesn't work, and the error bars are larger.
Yeah, which is like that plot that I showed.
Okay. You just wanted to clarify there was a little bit.
Yeah, I should put like the name deep set or not. So. Should be.
Yeah. Another quick question. So I guess when you apply this to data, you will need to somehow incorporate uncertainties. And do you have some thoughts on how to do that on the model?
Not yet. We are trying to overcome like the steps that I showed you in the super sample covariance slide. So it kind of works for super sample covariance. It kind of works when we try to, I don't know, to change the velocities in 15%. These are the tests that we're doing right now. It's working, but I don't know, to incorporate the error in the measurements in a really formal way, yeah, we don't have this recipe yet.
Okay, let's thank Natali again